Hello everyone and welcome to another Stat 437 lecture video. In the video today, we're going to be talking about how we can actually go about estimating the parameters that we care about in our generalized linear marginal models. So in the previous lecture, we were talking about M-estimation, but before that, we introduced this concept of a generalized linear marginal model, or GLMM, and we talked about how to specify those models and how we can specify the models in such a way that we don't need a distribution to sort of capture all of the structure that we're interested in. But we left off in that lecture, having specified the models, but not having talked about how we can actually estimate the parameters that are of interest to us. And so in today's lecture, what we're going to do is we're going to take those concepts from M-estimation that we were talking about last time and apply them to these models that we care about so that we can actually estimate our parameters from our marginal models. And so sort of once again, today we're going to be looking at a high level overview, sort of the conceptual nuts and bolts of this estimation procedure. So it's going to be a little bit more involved as a video. But if you have any questions at all, if anything doesn't make sense, please reach out to me. And with that, I'll open up the slides here. So the first thing to sort of note is our review of generalized marginal models for longitudinal data. So if you recall, we specified a GLMM by using a link function, which links our conditional mean to the linear predictor. We specified a variance function, and the idea was that the variance of our observation is going to be equal to some scale parameter times by that variance function. And we also specified a matrix of pairwise association, so the correlation structure, right? And we basically said we can model any type of data that we care about by specifying these components, and that's sort of all of the structure that we're interested in. So sort of put succinctly, we take g, which is some link function of our conditional mean, and we set that equal to xij times beta, which is our linear predictor. We specify the variance of yij to be phi times by some variance function, which is a function of the mean. And we define our correlation to be some matrix, which can be a pattern matrix or it can be unconstrained. And the idea is that we want to be able to estimate the parameters, so the beta, in this model. Also recall that we talked about M-estimators. So an M-estimator, we defined this function u, and we said u of theta or u of theta and y. And the idea was that it's a function where we take a summation over an IID sample, right? So here I have it written as a mean over an IID sample, but you can remove the 1 over n, that's fine. It doesn't sort of change anything meaningfully. And so when we have a function that is a sum over an IID sample of some function, and we solve for our estimator by setting this equal to 0 and solving, that's an M-estimator. And when we're using an M-estimator, then we get these properties that theta hat is consistent and asymptotically normal, wherever we're sort of looking at an unbiased estimating equation. So we looked at some examples of that in the last lecture. There's some examples posted on the course website. And so the idea that we're going to be looking at today is how can we take that theory of M-estimation and apply it to actually get parameter estimates for our marginal models. So if we can form an M-estimator using just what we specified from the GLMM, then we would have sort of a way of estimating these parameters, and we'd also get a lot of asymptotic theory for free. So why don't we go about trying to do that? So recall that we've specified a link function which connects the conditional mean to a linear predictor. So right here, this g of mu equals x transpose beta, that's going to be sort of the core piece of this model, right? Because we're mostly interested in how does this mean response change over time. And so because of that, this is our core piece of our core focus here, right? And we're not making any assumptions onto the distribution of y, but we are going to be sort of making this the structural assumption about this link function in the mean. So equivalently, we can write this assumption as the mean is granted by g inverse x beta, right? And so we'd have to make sure that we're selecting a link function which is invertible and which is nicely behaved. But this link function linear predictor connection here is equivalent to us specifying this relationship for the mean of our random variable. All right, and so the idea is, we're starting with this mean specification. And so we saw in the last lecture that if we took an M-estimator that's basically, our observed data minus the parameter we're interested in, and then we set that up as our M-estimator, well, that's going to work to create an unbiased estimator, or an unbiased estimating equation. And so here, if I define this phi ij equal to yij minus g inverse of our linear predictor here, right? And so in other words, all I'm doing is I'm saying yij minus what we specified as the mean, right? So it's yij minus mu ij. Well, we can think about forming the M-estimator from this equation, right? So if we take the expected value of this, again, this expectation, and we can do it expected value conditional on xij because we're sort of taking that as fixed. Well, we're going to have the expected value of yij given xij minus this g inverse term. But we're already saying that this conditional expectation is equal to this. And so if we've specified the correct mean function, then when we have the true beta plugged in to this phi ij equation here, it's going to have expectation 0, right? And that's exactly what our parameter was or the requirement was to have an M-estimator that's consistent. So this suggests using this sort of equation as an M-estimator, right? If we sum over our data, and at each point, we take yij minus g inverse of our mean structure here, well, this is going to be an unbiased estimating equation that we could solve equals to 0 for beta. And based on M-estimation theory, that's going to provide consistent and asymptotically normal estimators for beta. Now, we could equivalently do this as a multivariate problem here, right? And so this is actually probably a more natural way to think about it in terms of this longitudinal data here. But here, all we're doing is we're saying that if we have this mean relationship that we're confident in for yi, right, then this is sort of the most basic estimating equation that we could think of framing that's going to be unbiased for our parameter, right? And so something as simple as this would actually work. We could actually use this and estimate beta from it. And if you notice, the only thing that we've been required to specify in order to get this is this mean relationship. So this would be an estimator that gives us the correct beta parameters, and the only thing that we need to specify correctly is this mean relationship. And I'd like to pause on that for a second and think about sort of how powerful that is, right? We've not specified a distribution for our outcome. All we've done is we've said we think that the mean of the outcome follows this form, and from that, we have an estimator that's not only consistent, but it's also asymptotically normal, and we know exactly what the form of the variance of our estimator is going to be, right? So that's sort of this incredibly powerful technique. Now, in actual fact, we're not going to use this estimator specifically, but it would work, and it's a way that we can think about working from a generalized estimating equation, and that's the estimation technique that we're going to be using. The issue with this is that it's not going to be the most efficient estimator. So if you look at the asymptotic variance of it, it's going to be higher than it needs to be, and that's because we're sort of not using as much information as we might be able to. So instead, we propose this generalized estimating equations, or GEE approach. And this is a widely used approach. You can use this approach sort of in GLMs directly. It's well studied, but for our sake, the GEE approach sets up this estimating equation here, which takes a matrix di transpose times by the inverse of our working covariance matrix, and then multiplied by yi minus gi, or g inverse xi beta, right? And so this second component that we have right here, this component is essentially the piece that we specified as a possible M-estimator on our previous slide. And so when you're bringing in these two terms out front here, all they're doing is they're working to lower the variance of our estimator. And so we're specifying our working correlation matrix or our working covariance matrix. And in this case, di is just going to be a matrix, which is the derivative of our mean with respect to the parameter beta, right? So this is the derivative of mu I with respect to beta, but we know that mu I is g inverse times g inverse of our linear predictor, right? And so di is just a derivative matrix. It's going to be k times p in dimension. we have VI as a working covariance matrix. And just recall from when we were talking linear marginal models, we can write this out as AI square rooted times by RI times by AI square rooted, where AI is just capturing the individual variance terms, right? And so basically, between this assumption of our mean structure and link function, right, which we take in up here and defines our D, with this assumption of our variance function and Ri, so the correlation matrix, now we've specified a full estimating equation. And this estimating equation using M-estimation theory is going to provide consistent and asymptotically normal estimators for the parameters of interest. Typically, we're going to take VI to be a function of our mu's, and it's going to depend on exactly what type of data that we're looking at. So the first point that I want to make is that this is essentially just quasi-maximum likelihood, right? If you actually look at the quasi-maximum likelihood estimators, they're doing basically this situation here, right? Out front, in a quasi-maximum likelihood estimator, we have the derivative of mu with respect to beta, which is exactly what D is. D here just happens to be multivariate, but it's the same thing. Then we multiply by the inverse variance that we've specified. And then we multiply by the difference between our mean and, or the difference between our observed value and the mean of our specified model. And so the reason we reviewed quasi-likelihood theory was to actually get us to the point of being able to specify generalized estimating equations. So they're sort of just a more general version of quasi-likelihood estimators. In the next lecture, I'm going to actually walk through a handful of specific examples for this. So we'll look through continuous data, binomial data, and count data, and we'll actually see how can we write down the specific form in each of those scenarios. So if you need sort of more tangible examples, we'll be looking at those shortly. But for now, just remember that from M-estimation theory, this provides us a very powerful form of formulating these estimators. And part of the reason is that we get asymptotic inference sort of directly from this specification. So recall that because these are unbiased estimating equations, we're going to get that our beta hat is going to be approximately asymptotically normally distributed. It's going to have a mean of the true value parameter, and we're going to have this variance matrix, right? And right here, what we're doing is we're writing this variance matrix as J inverse times by gamma times by J inverse transpose. So in M-estimation in general, we were calling those the A and B matrices. The same thing here, it's just that standard notation would have us using J and gamma. And so we can actually find that these take on a particular form, right? And so this form is coming from, we said that the A matrix was the expected value of the negative derivative of our estimating function. And this is going to work out to be the sum of di transpose vi inverse di. And then this gamma is going to be the variance of our estimating equation, which in this case takes on this form of di transpose vi inverse times by the variance of yi times by vi inverse times by di. Now, one thing to note is that here we can see that we have the variance of yi as a term in this gamma matrix. This is the true variance of yi. So if you remember, we're using this notation vi to capture our working covariance matrix for yi, but we're acknowledging that we might not correctly specify it. This will simplify down quite nicely if you actually have the case that vi is the same thing as the variance of yi, right? Because if vi is our variance of yi, then you're going to get this cancellation between this vi inverse and the variance of yi. And so then it simplifies down, and you'll actually find that J and gamma in that case are exactly the same matrix. And because of that, when you write this out, we'll have J canceling with gamma, and you'll be left with just J inverse as our variance matrix. And so there is some simplification that can sometimes happen here, but that's only happening when VI is correctly specified. If VI is not correctly specified, this is all still valid. And that's another really important point. The only thing that we require in order for this to be valid is that our mean, which means our link function and our linear predictor, is correctly specified. Everything else is just going to help with the efficiency of the estimators. Now, we also have two additional parameters, right? We have the rho and we have the phi. Now, these are the correlation and the scale parameters, respectively. And generally speaking, we're going to think of them as nuisance parameters. We don't really care about them. And that's because when we're fitting these marginal models or these generalized linear marginal models, our focus is really on how does the mean relate to the variates that we care about. Okay? And so everything else is just sort of getting in the way. And GEE is such a powerful method because it really only requires us to have this mean correct. But in order to actually do the estimation in an effective way, we do need these other parameters. And so typically what we're going to do is we're going to estimate them in this ad hoc way after the fact using Pearson residuals. So this part's not super important, actually. You don't need to memorize these equations or anything. And they are provided for you in the notes that are online. But the idea is that we can take these standardized residuals here, right? So we have yij minus our estimated mean, mu ij. And then we scale that by the variance, the estimated variance, right? So our variance function with mu ij plugged in, or our estimated mu ij. And so this gives us essentially a scaled residual value in the same way that we would be thinking of scaled residuals for linear regression or generalized linear models. And then using these, we can plug these into these formulas that are going to be estimators for phi and rho. And so this should be a lowercase n, that's our sample size there. But the idea is that we have these estimators that are essentially formed as method of moment estimators that give us consistent estimates for our rho parameters and our scale parameter. Okay, and so with these estimated, then we can actually plug those back in and get estimates for our values of beta hat. So the way this process is actually going to work, it has to be iterative because none of these equations can be solved sort of explicitly, right? But so we start off with some initial value for beta hat. Then we use that initial value to compute these ad hoc values for phi hat and rho hat. And then we're going to plug those back in and solve our estimating equation for beta hat again. Then we use that new version of beta hat to update the parameters of phi and rho, and then we repeat this process over and over and over again until our estimates converge. Okay, and so generally speaking, these are nuisance parameters, but if you do require the estimates of them, we can do that using sort of a residual analysis. Now, because of asymptotic normality, because the M-estimation theory, we can use wald-based procedures. And that's going to be the core way that we go about doing inference, right? So we saw that with the linear marginal models. We saw that in linear regression and in generalized linear models as well. But anything that is based on a wald-type hypothesis test, so that's, taking beta j is approximately normally distributed, and then you can use the standard error of beta j to form confidence intervals or do hypothesis tests. All of that is still valid in the case of generalized linear marginal models, right? Now, one point to note is that we cannot use likelihood ratio procedures. The reason is that generalized estimating equations are not a likelihood procedure. So there is no likelihood. We're not maximizing a log likelihood. There's nothing related to likelihood in this estimation procedure. And so what you can't do is do that nested likelihood ratio testing that we've been doing before, right? So you're not able to do that if you're using GEE, but we are able to use wald procedures still. And so we're going to sort of take advantage of that. Now, there is this idea of a generalized score statistic, which is sort of an extension of the likelihood ratio procedure to generalized estimating equations. Okay, so I'm going to put down the whole procedure here. I'll note this last line first. You don't actually need to learn this. And the reason that you don't need to learn this is twofold. First, we have our wald procedures, and we're going to focus on using wald tests and wald-based confidence intervals and everything else. Now, generally speaking, these procedures are not implemented or they're not implemented well in standard statistical software. And so because of that, this generalized score statistic tends to be ignored. However, if you do want to use it, you're totally welcome to. And the general procedure is no more difficult than everything else we've been doing. So we're thinking about a standard, multilinear hypothesis here. So we have some matrix C, beta equals 0. And the idea is that we can compute this statistic here. And so this statistic has a form that's rather unwieldy. I wouldn't advise memorizing it or anything, but you're essentially taking the estimating equation, you're plugging in an estimated value of beta, where the idea is you estimate this value using GEE when you assume that the null hypothesis is true. So that's this beta tilde G. And then you multiply it by some matrices, and then you multiply it by the estimating equation evaluated again. And under the null hypothesis, this is going to be a chi-squared R distribution, right? So here, for this form, beta tilde G is the GEE estimator, assuming that the null hypothesis is correct. And these two matrices are actually just those variance, asymptotic variance matrices we were just talking about, right? So you can plug all of that in, and that expression is going to have a chi-square distribution with R degrees of freedom, where R is the rank of our C matrix. So it's going to be essentially exactly like what we were doing before. The only difference is this is a far more difficult form to learn, and it's not typically implemented, so you do not need to actually use this. The other point is that BIC and AIC both rely on likelihood, and so neither of them are valid, but we do have this quasi-information criterion, so QIC, and it's going to perform exactly the same as AIC or BIC would. So you want lower values of it if you're trying to do model selection. So that's the other alternative here. So basically the summary is all of our asymptotic inference is going to be the same, except we can't use anything that's based on the likelihood. So we have to rely on Wald-based statistics, we can rely on these generalized score statistics, or we can rely on sort of this quasi-information criterion to make our decisions, but otherwise procedures are all exactly the same. So one other point, and I've made this a few times, but I'm going to harp on it a little bit further right now, is that inference is valid even if our variance matrix is misspecified. In fact, inference is valid as long as we have the mean model correct. So why do we even bother specifying a variance matrix, right? If you think, if we go back here a little ways, if we just can take VI to be anything we want it to be, why don't we just take it to be the identity matrix, right? Why even include it here? So there's a couple of reasons for this. The primary reason is efficiency. So if you do not specify the variance model, you're not going to have any bias asymptotically. You're not going to have any problems with consistency. But in a smaller sample, you're going to have larger variance than you want. Even asymptotically, you're going to have larger variance than you want. And so the basic premise is by specifying this variance, if we get it wrong, we lose nothing, right? Because our estimators are still going to be fine. But if we can manage to specify that variance correctly, then suddenly our estimators are going to perform better in smaller samples, and they're also going to be more efficient even when we take a very large sample, right? And so it's sort of this no-lose situation for us, where by specifying this, we're just adding extra efficiency to our estimator, but it doesn't cost us anything in terms of robustness, so there's no reason not to specify it. But what it does mean is that we don't have to be super concerned about getting this right. You know, if we want to take a variance assumption that's based not so much on what we think might actually be true, but that's based on something that's easy to work with, easy to estimate, computationally simple, we actually have the flexibility of doing that as long as we're acknowledging that our estimators aren't going to be as efficient as they otherwise could be. Okay, so that's why we bother with specifying VI, even though we don't technically need to. So the next point here is parameter interpretation. And this is a key point and sort of going to be, a point that we stress going forward. And that's marginal models are models for the population level effects, right? So if you think about what we're actually fitting, we're saying the expected value of Yij given Xij. Any person in the population who has the same level for Xij is going to have sort of the same expected value here, right? We're averaging across the whole population. And because of that, we have to interpret all of the betas that we estimate as population level effects, right? And so beta j is going to have some impact on average across the whole population, right? And we've seen how we can interpret those. It's going to depend on what the factor is that you're changing, but it's always going to be something like beta j represents the expected change in our mean given a unit increase in the factor we're talking about, holding everything else constant. But it's really important to know that these are not individual level effects, right? Nothing in this model can be interpreted at the level of the individual, okay? And so because of that, that's sort of one shortcoming of these models here, of these GEEs. But as long as you're interpreting things at the population level, that's going to be the point of inference that we often care about in these surveys, right? So if you want to think about how does, aging impact your propensity to develop dementia, which was the sort of the starting example, well, that's actually at the population level that we care about it. We don't care about any one specific person, but we care about on the whole, how does aging impact dementia? Same thing with the COVID example that we were looking at. If you want to know how many new cases of COVID are going to be in a particular region, well, you're actually probably modeling that based on sort of the average across the region based on sort of the region's parameters. And if two regions have very similar population structures, whatever factors you might be including in that model, then you're going to say that they're going to have expected similar number of cases and so forth, right? So parameters have to be interpreted at the population level. Now, there's one other point that I want to make here, and that is discussing time-varying covariates, okay? In a linear marginal model, or a generalized linear marginal model, the structure that we're assuming for this model is actually making an implicit independence assumption. So in particular, without sort of explicitly specifying this, we are assuming that the mean Yij, or sorry, the value of Yij is going to be independent of all of the variates that we're including, except for the variates measured at time j as well, assuming that we have those, right? So put differently, Yij is independent of xik given xij for all j not equal to k. So what we're saying is that the outcome is conditionally independent of all other explanatory factors given the current time points explanatory factors. So this is going to be true in general if you have a factor which is time invariant, right? So if you have something that does not change over time, so for instance, you enroll people in either a placebo or a treatment group, and they're in that for the whole study, then this is going to be true because, of course, if you're already conditioning on which group they're in, which will be inside of the factor at xij, then you don't need to know what they were in at time k. This is also going to be true of deterministic factors. And so if you have, for instance, time as a factor in your model here, right? Well, we know that time is changing deterministically, right? So every new observation is going to be at some set time point. And so that's not sort of an issue because we can always predict what xik is going to have there just by knowing, sort of what is k. It's not going to be true of factors that change stochastically over time, right? So if you have a factor such as someone's body weight, for instance, this is going to vary over the course of a longitudinal study, and it's not going to vary deterministically. It's going to be sort of random fluctuations. And those factors can't be included in these marginal models. You can actually work out sort of why this is based on the this independence rule here, but I can also use sort of an example here to discuss why this is going to be a problem, right? So here we're looking at, say, blood glucose levels, right, as our outcome, and our explanatory factor is the amount of physical activity that was taken, right? And so we have 2 time points here, and we want to know how does the amount of physical activity impact someone's blood glucose level, right? And so at time 1, it's not a problem. We have, can infer how active were they, and sort of what is the impact on the blood glucose level. However, there's this observed phenomena, which is that whenever someone has an elevated blood glucose level, that forces them to start working out more or to have higher physical activity in the next period, right? So if Y1 is elevated, then we increase X2, right? So you can see that this Y1 is going to be predicting X2, right? So if Y1 is high, then we'd expect X2 to be slightly higher. And so as a result, Y1 is not going to be independent of X2, even if we know what X1 is, right? Because Y1 is going to be influencing X2. And so then the problem with trying to sort of fit a model with these data based on what we're looking at here is that it becomes hard for us to determine how much of the effect that we're observing is actually sort of this hidden effect of our outcome changing the future value. So you're going to need sort of more complicated techniques to deal with this. The data that we're looking at in the class, this isn't going to be an issue for it, but it is something to watch out for if you're trying to apply these models sort of in the real world. So in summary, generalized estimating equations are a way for us to solve for the beta parameters in a marginal model. The procedures result in asymptotically normal and consistent estimators, and we get all of this for free from the fact that these are just M-estimators. The parameters in a generalized linear marginal model are interpreted as population averaged effects, not individual level effects, and we need to be mindful of time-varying covariates, which are stochastic in nature. We don't have to worry about time-invariant covariates. We don't have to worry about deterministic covariates. We just have to worry about those time-varying covariates, which are stochastic. And so with this, we can now sort of fit any model that we want to, really, to these longitudinal data that we might be observing, right? And so the idea here was that we took a generalized linear marginal model, which only specifies a mean link function, which sort of gives you the mean, as well as your variance and your correlation structure. And using those, we can combine that with M-estimation theory to get consistent estimators, which are asymptotically normal, that we can provide inference on. So with this, if your target of inference is the population, we now have a set of models that will work for just about every question you could want to ask, right? We can do all of the same types of analysis that we performed on continuous data, whether it's count data, whether it's binary data, whether it's categorical data, all of this. As long as we can specify a mean structure, variance, and correlation, then we can do this estimation procedure. So in the coming lectures, what we're going to do is we're going to see some of this theory dived into in a little bit more detail. We're going to see some specific examples of setting up the estimating equations, and we're going to apply this to a few data sets, seeing how we can use these R packages to actually estimate it, which will give us, practice with estimating parameters, with sort of looking at how we perform hypothesis tests, how we do inference. But I really do want to stress that right now you sort of have the tools to start analyzing real longitudinal data, but only when that data you want to analyze at a population level, right? So then after we sort of finish talking through these applications of marginal models, then what we're going to do is turn our focus towards trying to do analysis at the individual level, right? So where we can actually estimate these individual effects. And so I hope that all of that made some sense. Again, we're going to dive into some more detail with all of these topics in the coming lecture. So if it didn't make perfect sense, that's okay. We'll go over this a little bit more as that comes. But as always, if you have any questions at all, please let me know, and I will see you all in the next lecture video.